Hello, Pamela.
Hi, Fraser.
Um, so we're going to, if anyone has never done this before, what we're doing is we're doing a live episode of our weekly podcast, Astronomy Cast, and so you'll see us record, warts and all. It'll take us about half an hour to get through the show itself, and you'll sort of see what goes into doing the show, all the mistakes that we make, all the times where Pamela pronounces things funny and I have to
All
fix
the
her
times.
pronunciation.
You never do that.
And yeah, and then all the times when I decide that my question was terrible, we need to go back and ask a different question. Yeah, and all the times that someone shows up at the front door, and so someone has to go and sign for a package. So yeah, so that's what we'll get to today, and then we'll stick around for a few minutes afterwards, and people can ask us some questions. Now you'll hear me say that it is for May 13th. That's because we're still catching up. We did 5 episodes last week. So we're catching up like crazy. We got 3 planned this week, so that'll put us within striking distance of being fully caught up. We would do more, but you've got a kind of madness this weekend.
I have a madness this whole week.
The preparation for, and then the execution
right.
of.
Well, and I'm getting Google Glass this week, so
just keep it in a box. Don't go anywhere near it.
So this weekend is our Google Hangout-a-thon to try and raise money for science communications and education through CosmoQuest. So starting at noon Pacific, starting at 9 a.m. Pacific, noon Eastern, 11 a.m. Central. Do the math for your time zones the rest of the way around the globe. We are going to start 24 hours of madcapped hangout-a-thon goodness. We're going to bring in musical guests, the Jungle Fire. I have their CDs right here. They're a group that does soul music that is science-bent. I just love the twist of that. We're still working to line up some additional musical guests. We're going to have Mad Art Lab's Dead Puppet Death by Puppets. We're going to do a virtual star party. We're going to bring on the cast of Beyond the Wall to try and figure out what the heck is this science that explains the weather of Game of Thrones. And it looks like our 24 hours is actually going to be 36 hours.
Oh,
our
come
goal
on.
Well, we keep getting this great outpouring of people who want to help. And yeah, we usually call that a normal weekend, staying up that long around here.
Right.
And we're also going to be releasing the latest version of the CosmoQuest interface. So it's going to be a crazy weekend, and it's going to be co-hosted by Nicole and I. We're going to be having you come on a bunch, and it should all be good.
You know what's funny? I don't see all of the times that you want me to do things, which makes me feel like you plan to have me show up at all kinds of times. So
no, so we haven't finished booking everyone yet, and you have a flexible schedule. So you're on the to be scheduled last.
Sure, no problem. And I know we might do some stuff at night with some astronomers, and we might also do some stuff during the day.
Yes.
And sometimes someone's day is another person's night. So I think maybe try and catch a live ISS pass, things like that. So
yeah, and I'm switching cameras just to warn you. Switching, that sort of worked.
Why'd you do that?
Because this camera is the camera that you prefer, except it has a crazy tilt and is just out of arms.
Yeah, and your video has frozen.
Oh, it did?
For me, anyway. That's okay. I don't, as people didn't realize, I don't, now you're back. I don't actually look at your video during the show because it's too distracting. Okay, cool. So, and one other last piece of news, which is Quarks and Quarks, which is a science radio show here in Canada on CBC. And if you're a Canadian who loves science, then you absolutely know what Quarks and Quarks is. They're doing a live show tonight at 7 p.m. Eastern Time. They're going to be answering questions, and I'm going to be jumping in and helping Bob McDonald answer a question about space.
Awesome. That's one of my favorite shows.
I know. Me too. And so I saw they're going to do this live hangout, and I'm like, oh, I've done hundreds of these things. Can I help you out? and they said, oh, why don't you help Bob answer questions? So that's tonight at 7 o'clock Eastern time, 4 Pacific. They're going to be doing a live question show with Bob McDonald, and it's going to be awesome. So yeah, if you love Quirks and Quarks, this is great to see them jumping on the Google Plus train, and I'll help them out. Which is like a dream come true for me. It's like the full circle, which is great.
Radiolab, that's the only one you're missing now.
Yeah, Radiolab. Could collect them all. Okay, cool. All right, so once again, so if you want to comment, which I can see a ton of people are now commenting, and a couple of people are having some problems with the technology, which is too bad.
We're sorry.
We're so sorry. So you can make comments or questions on the event page if you're watching it there. You can make comments and questions on, so if you're watching this on my stream on Google+, if you're watching this embedded somewhere, you can just use Twitter, just use the hashtag AstronomyCast, and you can also comment over on YouTube. And as we always say, if you feel like your comments are not getting noticed, then you might want to switch over and do the comments on YouTube, because that's sort of the most safe and stable place for the comments. Although today not so much, so who knows? Cool. All right, are you ready to record?
Hopefully.
Okay. Well, I'm going to press record.
I am looking for where I put the window. There it is. I have pressed record, and it is recording like a mad demon.
In mono. Perfectly.
In mono.
Super stable. Good old dependable GarageBand. Nothing wrong with that.
It is on this computer.
All right. Ooh, I got the number wrong. That would be embarrassing. Hold on.
Okay, I'm going to stop the recording.
Really? All right.
Yeah.
Okay, I will stop mine too then.
Torturing Preston isn't on my list of things to do today.
Try to, if we can, yeah, all right. Okay, say when.
Okay, I am pressing record, and it is recording like a mad demon yet
All right,
again.
I have also pressed record. Here we go. Astronomy Cast, episode 306 for Monday, May 13th, 2013, Accretion Disks. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing great. Weather's improving. I went out last night with I got a new lens for my camera. I got a 14 millimeter 2.8 lens and captured some wide field astrophotography. And
is it a lens with a rectangular field of view still?
It's a little fisheye. It's a little bit fisheye. Is that what you mean, or
no? So like with my fisheye lens, it's actually a round part of the detector that it uses. Does yours fill the detector?
I think it's cropping a little bit.
Okay, that's still cool.
Yeah, but it's so fast. I mean, I kept turning it down and just kept getting this beautiful shot of the Big Dipper. So I haven't really explored it. And tonight there's going to be this potential for a chance meteor shower. So I'm going to try and go out tonight and see if I can get some meteors on camera.
That's awesome.
Yeah. Now it's probably too late for us. By the time people hear this, we've already done the 24-hour hangout-a-thon for CosmoQuest. But if we haven't, June 15th this
16th.
weekend. 16th, 24 hours of fundraising space madness on Google+.
And it's never too late to donate. We actually really need your donations to keep our programs going. We're facing a lot of funding cuts, and we've seen a radical drop in donations for Astrosphere New Media this year.
Yeah.
So if you go to cosmoquest.org/donate, you can see the links to donate both for citizen science and to keep media like Astronomy Cast going into the future.
Perfect. All right. Well, enough talk. Let's talk space. So when too much material tries to come together, everything starts to spin and flatten out. You get an accretion disk. Astronomers find them around newly forming stars, supermassive black holes, and many other places in the universe. Today we'll talk about what it takes to get an accretion disk and how they help us understand the objects inside. So what do you think is like the classic example of an accretion disk? I always use as sort of like an analogy my bathtub drain.
Really?
Does that make sense? Because you get your bathtub, you get tons of water in the bathtub, and then the water is trying to go down the drain, and it backs up and starts to spin. And I guess flatten out?
I would never have got there from here.
Really? Okay, well, that's my analogy.
Sorry.
Too much water to get down the drain, and so you get
No, it's a perfectly good analogy. It's just not one my brain went to, and
So,
that's cool.
so what's your
Um,
analogy?
so I have to admit I'm enough of a geek that for me it's flattened like a spinning pizza, except in this case it's usually a hungry object like a black hole that's stripping material off of a nearby neighbor. So it's a cannibalistic spinning piece of pizza.
So what are the forces involved? What are the environmental conditions that we require for us to get an accretion disk? And
It's
what's
based
going on?
an accretion disk forms anytime you have a microphone that's on a really loose pivot. Sorry about that.
Yeah, yeah.
Uh,
Or
it,
or an actively tuning black hole, you know,
yeah,
microphone or
sorry
black
about that,
hole.
Preston. I just bumped my microphone with my hand. Um, no, so in reality, any time that you have an accretion disk, what you have is some sort of a um, hole, whether it be the hole that's quite literally in your bathtub or the gravitational low point that's in the three-dimensional map of space using gravity that things are trying to fall into. So as things fall down the gravitational well, as they fall down the drain in your bathtub, conservation of angular momentum prevents them from actually falling straight down. So if you have even the slightest velocity to the left, right, above, or below that potential well that things are trying to fall down, it's going to end up spiraling in instead of falling straight in.
And you know, I mean, you can have this what seems like just a perfectly content cloud of cold gas that doesn't seem to have any momentum in it, but it's when it starts to come together that it gets that rotation happening, right?
And so what you're talking about, I think, is the type of disk that forms in the solar nebula model
Yeah.
when you're forming a solar system. And in this case, you have a giant molecular cloud of stuff. And if you're able to somehow destabilize that giant cloud so that you only affect its center of mass. You hit it neither to the left, right, up, down, anything else of its center of mass. You simply provide the force to the center of mass. You might be able to get it collapsing straight in. But there's really no way to do that in the real universe that we live in. So the reality is, however you bump, however you destabilize that giant molecular cloud, you're going to end up imparting rotation so that as it starts collapsing, it starts also rotating. And that collapsing and rotating system ends up flattening into a disk the same way pizza dough flattens into a disk as you throw it up and set it spinning.
And so what are the constraints, or what are the, I guess, what are the environmental factors that are going to define, like, let's go to the black hole example, right? So you got your black hole material, it's destroying some cloud of gas or a star or something else, and this material is falling into it. What's going to define the, I guess, the size of the disk, the speed of its rotation, the temperature of it?
Well, so let's break these down one factor at a time. So let's start with the case of you have a single black hole and there's a single small measly red dwarf star that's about to seek death on the surface of the black hole for some reason.
Yeah.
It happens.
Yeah.
So we have the star falling toward the black hole. And this is something that you've actually seen probably a model for at a science museum, where you have that funnel-shaped curving thing at the front of the museum that you're encouraged to put coins into to raise money. And as the coins roll around, they go faster and faster and faster as they get towards the center. Well, with that black hole that has the red dwarf falling towards it, as it comes in, it's going to end up going on ever-tightening spirals until eventually the red dwarf first gets close enough to the black hole that it hits its Roche limit. It hits the point at which it is no longer able to gravitationally maintain itself as a sphere. And as it gets closer and closer, it's eventually going to get shredded apart, spaghettified, just like a human being would as it falls in, turned into this long stream of atoms. And as those atoms now wrap around and around, you can imagine them forming a donut around that black hole. In this case, this disk that's very tiny of this one star's material may actually end up forming inside the event horizon as the material works its way in towards that inner singularity. So here the key is object falling in can't fall straight in because it has this angular momentum, and so it ends up spiraling in, um, getting shredded along the way, and then eventually death, spaghettification, and death.
Right. But why? I mean, I guess why do you get that disk forming around the black hole? Why doesn't it just gulp and that's it? Star goes in and that's that.
Well, the star can't just go in. That's the thing. Is it if the star just happens to be that its velocity has it perfectly so that its center of mass is perfectly aligned with the center of mass of the black hole,
Yep. Boom.
then
Direct hit.
right. Any other case, conservation of angular momentum says that some of its velocity is going to try and put it into orbit instead. But the orbit is going to be a decaying orbit in most cases when you have black holes to deal with. If the velocity is trying to carry it past the black hole initially, it will probably end up in a death spiral instead. Now, as the material gets stretched out, you can imagine it initially forms a comet. Then it ends up forming a single ring. And as the material spirals in, it's getting to be a longer and longer spiral that forms essentially a disk. So think about coming in with a highlighter, and you're drawing around, and as you spiral in, some of the material is disappearing as you draw. So it's like it's disappearing ink or something. But as you draw faster and faster with smaller and smaller circles, that material gets distributed out into a band around the black hole. Am I making sense?
Yeah, you are making sense. And I guess the thing is that with a lot of these, we see these quasars and active black holes, these accretion disks can get quite large. And
those are not a single red dwarf star forming.
No, of course not. No. I mean, that was, I've switched from a stellar black hole, to a supermassive black hole. But even around a stellar mass black hole, if it's in a very, if it's in a all-you-can-eat, star cluster, that material is going to pile up, right?
Right. So.
And then heat up.
It's a matter of, as the stuff comes in, you just threw all these different things together that don't fit together. So I'm going to try and pull all these different variables apart.
Sure.
So we can have an accretion disk formed when a regular everyday star is forming. In this case, you have a giant molecular cloud that's in the process of collapse. As it collapses, the center heats up, forming a star, and there's a disk of material around it that tries to spiral all the way in to die. But eventually the radiation pressure of the forming star will stop that and start blasting things outwards instead. So that's a very simple accretion disk. In this process, all of the material involved came from that initial molecular cloud. Now, you can also end up with an accretion disk when you have a compact object, a white dwarf, a neutron star, a stellar mass black hole that's next to another normal star, a red giant, a main sequence star, just everyday star happily burning something into something new in its core. In these cases, if those two objects get too close, you end up with a cannibalistic white dwarf or a cannibalistic neutron star that's sucking material off of that nearby star. It's said to fill its Roche lobe, and the material is able to gravitationally escape and get pulled on to the other star, but it can't get there directly, so it instead spirals in. So in this case, you have the gravity of that compact object pulling an expanding stream of material off, and as it continues to eat the material, you end up with a disk that's getting larger and larger. It's getting denser as more material packs in. As it gets denser, it's actually able to reach the point where nuclear processes can start happening in that disk, in which case it might explode in a fury of nuclear reactions. So you end up with accretion disks in the situation of binary systems. These are called cataclysmic variables in general. And then, of course, you have the supermassive black holes, and they're eating everything from stars to planets to massive amounts of dust and gas that are falling in. And that material generally gets gravitationally flung in through a process of galaxies colliding.
And so, is the material that's piling up around the black hole, for example, I mean, you said that it starts to get like star, like almost the environment of star formation. I mean, it's a
Or
ferocious environment, right?
it's worse than the conditions of star formation. It's actually like the conditions inside a star. So when you're looking at a supermassive black hole's accretion disk in something like a quasar, an active galactic nuclei, in these cases you have a accretion disk that has many, 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 many stars worth of mass in it. And this vast accumulation of matter is gravitationally bound together by a supermassive black hole. So once nuclear reactions start happening in that giant disk, the disk doesn't explode and fall apart like it does in a cataclysmic variable. The accretion disk around a cataclysmic variable can actually essentially go poof, and then has to strip more material off of that nearby star so it can rebuild again and explode again. That's where the repeating aspect of some supernovae, not supernovae, some classic novae come up.
Well, I want to talk more about that, but we'll get to cataclysmic variables in a second. But
You're
I'd like
jumping
to
all over.
Yeah, no, I'm not. You brought up cataclysmic variables, not me. But no, just with the material, becoming like the inside of a star surrounding a supermassive black hole. That's crazy.
So yeah, it's just density. It's not crazy. I mean, this is the thing. These are completely logical relativistic objects. So they're hard to understand, but they make perfect sense if you understand general relativity.
Aren't there like two people in the? No, that's quantum physics.
No, that's
right?
string theory.
String theory, yeah.
This is completely straightforward. This is something they teach in a normal first or second year graduate course. It's a matter of you strip the mass off. It's bound together gravitationally. It gets sufficiently dense, nuclear reactions start going, nuclear burning starts going. This is why when you look at quasars, they have this extremely hot disk of material that's radiating its own light. That radiating its own light is coming from, in some cases, nuclear reactions going on inside the disk.
Yeah. And now one of the other factors that you get with these supermassive black holes is you get these jets. And with the accretion disk. So what's going on with the jets?
So the jets are a byproduct of having extremely hot material, in this case hot gas, gets rid of its electrons. It becomes ionized. It's no longer neutral. Anytime you have charged particles, so not neutral, charged particles that are moving in a circle, they generate a magnetic field. So this rotating disk of highly charged particles, highly hot particles, is going to create a magnetic field. And the strength of that magnetic field is related to how fast the material's spinning, how fast the entire disk is spinning, not individual atoms. So take that, and then also how much stuff is in that accretion disk. So when you have a massive accretion disk going around something like a supermassive black hole that will have massive amounts of gravity, accelerate it to massive orbital velocities, you end up with massive magnetic fields. So you have these extremely powerful magnetic fields that are flinging charged particles that get into that core out at relativistic speeds.
Relativistic speeds.
Yeah.
Yeah. And so, I mean, these things can push all the way across entire galaxies.
That's an understatement. You end up
across between galaxies.
Yeah, you end up with jets of material, radio jets, that are significantly larger than the galaxy itself. So when you look at the radio jets and you fit them into your entire field of view for just even making them in the background on your computer screen, the little galaxy in the center almost disappears for a lot of these systems.
Wow. And one of the theories, and I know you don't like the sort of, some of the more fringy theories, but is that some of these galactic jets may be responsible for periods of star formation in completely other galaxies.
Yeah, I don't have a problem with that one. That is simply gravitational interactions versus getting swamped by another galaxy's field. So in some cases, the jets flying off, you can actually see them compacting material as they interact with the intergalaxy medium, the intercluster medium. Yeah. And this compacting of material can lead to star formation. And if another galaxy makes the mistake of passing through one of these jets, that could regularly.
Yeah.
Not a big deal to form star formation and also ionize stuff as it goes.
Just added distance. You just
Yep.
like shoot another galaxy with your big laser beam, with your big jet. So that's really cool. So you started to sort of go to cataclysmic variables and all these other. So let's talk about some of the kinds of examples then where we're going to get these accretion disks. Now we've already talked about sort of black holes and the supermassive black holes, and you get the situation where the gravity of the black hole is tearing apart these stars and turning them into spirals and building up these disks around them. But wherever you get gravity, you can get these kinds of situations. So what are some other examples of where we get accretion disks in astronomy?
Well, to go from smallest to largest, it's thought that when the Jovian planets were forming, they probably had some sort of an accretion disk around them as they sucked material out of the protoplanetary disk that was around the sun. So you can have giant planets as they form actually having an accretion disk of material that's feeding them the hydrogen that ended up becoming the bulk of the gaseous planets. You can have any old star that's in the process of forming having an accretion disk around it until it gets hot enough to start blasting the material away.
Well, what about a situation like, we talk about how Mars with Phobos, because it's below the Roche limit, it's going to be torn apart in the next 10 million years or so and turn into a disk of material around Mars until it all crashes into the planet. I mean, is that sort of the same effect going on?
And this is one of those things where it's hard to think of that as much as an accretion disk, since it's not something that got captured from far, far away necessarily. As to think of it as an unstable planetary ring, but at a certain point that just becomes semantics.
Yeah, yeah.
So unstable planetary ring and accretion disk really, if you look at the physics of how they die, are about the same thing.
Right, in that you've got these gravitational tidal forces tearing something apart, putting it into a ring, and then consuming it. So now you talked about cataclysmic variables, and that's such a fascinating process. I want to sort of spend some time just talking about those. So what is a cataclysmic variable?
It is a star that is it's a compact object, a white dwarf, neutron star, black hole, something along those lines, that is capable of capturing material off of a neighboring star, a regular main sequence star, a giant star. And as the material gets streamed off of its neighbor, it forms a disk that periodically explodes.
And then what? When you say periodically explode, so right. So what's it's building up,
yeah,
and then it detonates.
Mm-hmm.
And what does the detonation do to kind of reset? How does it reset the system?
It just causes all of the material that was in the accretion disk to go up in essentially radioactive, not flames, but radioactive processes, and clears out the system to start all over again in some cases.
Is there some sort of end point to it? Will it go on forever, or
it can't go on forever because eventually it'll use up all the material in that neighboring star. But it will keep going as long as there's material that can be stolen.
And what happens when it does use up all that material? Then does it sort of finish off its? It just finishes off its meal and shuts down. It
finishes its meal. Yeah.
Yeah. Sorry, that's all we had to give.
Well, and it can actually go a rather catastrophic way, where you can have a white dwarf that, rather than politely blowing up the disk of material around it now and then, simply consumes it. So if you feed it just right, the material will build up on the surface of the white dwarf, and eventually, if the white dwarf gets too large, it will explode as a type 1a supernova, in which case it ends forever in a rather catastrophic way.
Right, and helps us understand the size of the universe.
Yes.
Right. Okay, so now what about protoplanetary disks? Because I think that sort of, we talked a bit about how Jupiter and stuff are forming, but this is sort of the whole method of formation of our planets, right?
Well, as I was saying earlier, it's just as simple as you have a large molecular cloud. It becomes gravitationally unstable for some reason. It begins spinning as it collapses. In the very center, you begin to form a star. And when that star lights up, instead of continuing to consume material around it gravitationally, that radiation pressure stops the accretion process and just leaves a protoplanetary disk behind.
A little piece of trivia here. Do you know what the study of accretion disks is called?
No.
It's called discoseismology.
I have never heard that, despite working with many people who study accretion disks.
This is just what Wikipedia says.
Okay.
Now it could be someone has hacked it, and
Or that's what they call
here you go.
one place.
Yeah, no, discoseismology and QPOs confront black hole spin. So now I just want to go back to black holes for a second because I love talking about black holes, and I know people love listening about black holes. Supermassive black holes are rotating in many cases at the very limits of, as predicted by Einstein, relativistic speeds. Does that have an impact when you reach essentially the final speed limits of the laws of physics? Does that have an impact on the accretion disk?
I don't think we have enough evidence yet to say. We're just starting to be able to use the observations that we have of the inner edges of accretion disks to start to prove, yes, we're pretty sure we actually are seeing evidence of black hole rotation. And so it's one thing to have theories that predict that, but we're still working on gathering up the evidence to know if these theories are true and to start to figure out if there are effects. One of the problems with studying accretion disks is, thankfully, there aren't any that are nearby.
Yeah.
So when we're studying them, we can't get the fine-grained measurements that we might want, and so it's hard.
Yeah. Wow. It's an amazing sort of process that we see in a lot of directions, and really it just comes down to if you have something that can be torn apart by some other center of gravity, you're going to get a disk.
And what I really like about working with accretion disks is it's the exact same physics across this huge parameter space of different masses. And it's one of those times where nature's basically allowed you to see the experiment run at the planetary scale, to see it run at the small star scale, to see it run at the large star scale, to see it run at all these different supermassive black hole-sized scales. And over, it's the exact same physics, just played out with a different twist.
So I could just use the same formula, whatever formula I learned the first time around, I can just apply it to the different object?
Yeah.
That is really cool. Awesome. Okay, well, thank you very much, Pamela.
It's been my pleasure, Fraser. Okay, and now we save.
Save.
So I'm recording in my home office today for the very simple reason that I wanted to keep watching the WWDC up until the very last possible moment. But one of the side effects of doing that is I forgot to turn notifications off, and this computer, unlike the one in my studio, has email on. And so it was like a plague of locust, all of these different messages coming in.
Yeah, distracting you in your brain.
Yeah.
I'm sorry, I was distracted by processing this episode that we just worked on. Okay. Yeah, so just a reminder that go out and try and see a meteor shower tonight. If you can get yourself to some dark skies, I've got an article up on Universe Today about this, but there's a possibly very sort of intermittent thing that could happen tonight. So I know that was very vague.
Why? So explain more.
Hold on, let me just get the details. Okay. Oops. Get the name of it. Come on, little buddy. All of our writers just hit us with a whole bunch of articles today. Universe Today is just booming. So I don't know if it has a name. The Gamma Delphinids. And back in 1930, we passed through a comet trail and got just a real burst of meteors. And so the time estimate is between 1 hour and 15, between 1 hour to 15 minutes. So essentially for like an hour, you're going to get this burst. But the burst is going to be visible in North America and South America. So, you know, we have no idea if this works. You know, I mean, you know, astronomers will predict 9 times out of 10 that we're going to see a meteor storm, and it's underwhelming. And then every now and then, it's amazing.
So we just happen to be passing through the right place this time?
At the right time. And so it's a small, I guess, trail from the comet, and so it's not like we pass through it every year at the same time. We're going to pass, you know, sometimes we're too high, too low, whatever, but this time we're actually going to pass through it, and it's going to be visible for like an hour.
That's awesome.
Yeah, so June 11th at 8:30 Universal Time. So that's about midnight. Pacific time, 3 in the morning.
10 p.m. Central.
No,
I went backwards.
It went the other way. Yeah, so it's going to be like
2
a.m. for
Central.
you, 3 a.m. for folks on the East Coast, and the Europeans are kind of out of luck. But, you know, I mean, just like if you've got dark skies, go out and look for some meteors tonight. It should be kind of warm and nice out. So you just got to be patient, which I am not. So, but I got this new lens I'm going to be testing out, so I'm going to see if we can see some meteors. All right, let me get to some questions here.
Okay.
I apologize to all the people who were not able to see the broadcast. I know there's some problems with the stream, so I'm sorry. It's clearly something's going wrong with Google, with YouTube today. Graham and Guido sort of have conspired to ask, how big can an accretion disk get? Are we talking solar system size or galaxy size? That's a good question. So when you have like an accretion disk around a supermassive black hole, how big is it?
It depends on when you are asking in the history of the universe. Early on, when we were still forming the supermassive black holes, it's thought that part of the way that we got some of the giant galaxies early on is there were these massive, somewhat chaotic systems that ended up having material getting driven in such that you had essentially galaxy-sized accretion disks that generated those first. So that would be small galaxy-sized, forming supermassive black holes that led to giant galaxies being around them.
So it's almost like the whole galaxy, these small galaxies were like solar systems. That you had, you know, at the core, you got the supermassive black hole forming, and then you've got this accretion disk of material around it, and within that disk, there's clouds of gas and dust, and those clouds of, and it would have just been gas, hydrogen gas, and those would be forming stars into star clusters, and right?
No, that part wasn't happening. It was, you simply had this chaotic disk that was the size of a small galaxy that was driven into forming the initial supermassive black hole and gravitationally pulling other material along. And over time, the radiation pressure from that accretion disk, in this case, it's the radiation pressure from the accretion disk, not from the black hole. Like in a solar nebula model, you have the radiation pressure from the star that ends the process. In this case, it's the radiation pressure from the accretion disk that ends the process of material coming in. And then the material that was in the outskirts waiting to become part of the accretion disk, kind of, it went into forming the giant galaxies.
Right. Okay. So Stephen Bourne asks, do accretion disks also suck up dark matter in theory?
I don't know. One of the things we're still trying to figure out is, do black holes eat dark matter the same way they eat regular matter? I'm not going to put my foot down definitively in this argument.
But so allow me to speculate. But I mean, the constraints here are, I mean, dark matter is definitely, affected by gravity from the black hole. And anything that makes it within the accretion disk, within the event horizon of the black hole is probably not going to escape. But dark matter doesn't seem to have this cross-section, and so dark matter probably doesn't get put into these accretion disks. They probably just pass right through them, So unless it's a direct hit on the black hole, it's not going in.
Right.
Is that my sort of, and that's like the lower limit, and then the upper limit is, yeah, maybe it does form into accretionists and all kinds of stuff, but
and we
just
don't know.
Yeah. But at the lower limit, anything that makes a direct hit on a black hole is probably going in.
Yeah.
If you make it within that event horizon, you are done for.
Yeah.
Okay, so Bastian Ruers asks, I'd like to know what you guys think about Mars 1 and other similar Mars missions that have been announced.
Oh, man.
Ooh.
I haven't prepped anything on that, so wrong question for the day.
Okay, well, I will opine about it.
Okay.
So I think it's awesome. I think, if some people...
Okay, so what are these missions?
So Mars 1, this is this sort of public... they want to send humans to Mars, and they're going to live there, and they're going to make a reality show out of it, and they're getting volunteers, and they're going to try and raise money for it, and it's madness. Right? So it is so ambitious that they're even planning this. I think it's probably not going to work. They're probably going to run out of funding. There's probably going to be lots of technical issues along the way, but it is demonstrating that there is this drive and demand and interest in this happening. And so I am all for it. And so I think that potentially, we're still probably 20, 30, 40 years away from this being a feasible technology that we can actually send humans to Mars and have them not die. And I hope that the people who are running this project are going to pull the plug if they can't get all of their technological ducks in a row here. That's my hope, right? That they're going to be like, oh, you know what? We can't protect them from the radiation, and this wouldn't be like the excitement of traveling to Mars. This would be the horror of watching them die on Mars. So I hope they'll pull the plug if enough of these technical issues don't come together. But I just think it's great that, it's like with the Arcade telescope, with what's happening with SpaceX, the next Chinese rocket's on the launch pad right now, and it's going to be launching. Planetary resources, tons of great stuff happening right now, and more equals better.
And this is where I have to admit that there's so many things going on that until they've actually had a successful launch, they don't exist.
Yeah, and they're so, I mean they're in the, hey, does anybody want to go to Mars? That's, that's the easy part. Right?
And it's not a matter that I don't have faith in them. It's just a matter of there's so many awesome things going on that trying to keep track of all of them could be a full-time job. And that's pretty much is Fraser's full-time job, is keeping track of all of this stuff for Universe Today. But there's so much amazing discovery being done that I have to throttle the content somehow, and one of the ways I throttle it is ignoring things that haven't had launches yet.
Haven't had launches yet, yeah. But yeah, so that's it. So it's, I think there's a lot of people attempting to come up with private solutions for being able to expand humanity out into the cosmos. And I'm, become a true solar system, an multiplanetary civilization, and I am all for that. And I think that's one of the great goals that human beings should set themselves towards, because as we saw with the Chelyabinsk meteor earlier, we are in a cosmic shooting gallery, and it's just a matter of time before some big asteroid comes along and wipes us out. It might be 60 million years from now, but still a matter of time. And so I think there's real value in us figuring out how to explore to other planets. And the only way to do it is to do it. That's it. You keep trying and go, oh, I see, we need to take more food, right? I see.
This is like some horrible version of the Oregon Trail where...
Yeah, exactly.
And your sister dies due to dysentery.
Yeah, right. Oh, okay. So next time we should, wash our hands better. Okay,
Man,
good.
I wish I had free time. I would write the video game instead of Oregon Trail, Mars Trail.
Yeah.
That needs to be a thing.
Yeah. I love that game, the Mars Trail. That's a good one. Oh, that's brilliant.
Don't steal it.
I'm not going to. I'm busy. So there's no way I could implement this. But I think that's a great idea, doing a Mars simulation video game where people go and, oh, everyone died of radiation. Oh, a solar flare.
If anyone out there listening wants to work on us with this, we'd love to share.
Yeah. Yeah. Okay. I'm seeing people are getting tons of problems, so I think we should just wrap this up.
Okay.
I'm sure this will fail to save to YouTube. But if it works, it works. All
Okay.
right, cool. Well, thank you very much, Pamela. And I know we've got 2 more episodes coming this week, so we will hopefully it'll be less
Yes.
problematic later on this week. Okay,
Hopefully.
we'll see you later. Thanks everyone for
Okay.
watching.
Bye bye.
That's okay. I don't,
That's
as people didn't realize, I don't. Now you're back. I don't actually look at your video during the show because it's too distracting. Okay, cool. So, and one other last piece of news, which is Corks and Quarks, which is a science radio show here in Canada on CBC. And if you're a Canadian who loves science, then you absolutely know what Quirks and Quarks is. They're doing a live show tonight at 7 p.m. Eastern Time. They're going to be answering questions. And I'm going to be jumping in and helping Bob McDonald answer a question about space.
Awesome. That's one
Yeah.
of my favorite shows.
I
I'm
know,
so
I know, me
jealous.
too. And so I saw they're going to do
Canadian.
this live hangout, and I'm like, oh, I've done hundreds of these things. Can I help you
Yeah.
out? And they said, oh, why don't you help Bob answer questions? So that's tonight at 7 o'clock Eastern Time, 4 Pacific. They're going to be doing a live question. 5 episodes last week. So we're
Yeah.
catching up like crazy. We got 3 planned this week, so that'll put us within striking distance of being fully caught up. We would do more, but you've got a kind of madness this weekend.
I have a madness this whole week.
Yeah, the preparation for, and then the execution
right.
of.
Well, and I'm getting Google Glass this week, so that
Just
I didn't.
keep it in a box. Don't go anywhere near it.
So this weekend is our Google Hangout-a-thon to try and raise money for science communications and education through CosmoQuest. So starting at noon Pacific, 9 a.m. Starting at 9 a.m. Pacific, noon Eastern, 11 a.m. Central. Do the math for your time zones the rest of the way around the globe. We are going to start 24 hours of madcapped hangout-a-thon goodness. We're going to bring in musical guests, the Jungle Five.
Hello, Pamela.
Hi, Fraser.
So we're going to, if anyone has never done this before, what we're doing is we're doing a live episode of our weekly podcast, Astronomy Cast, and so you'll see us record, warts and all. It'll take us about half an hour to get through the show itself, and you'll sort of see what goes into doing the show, all the mistakes that we make, all the times where Pamela pronounces things funny and I have to
All
fix
the
her
times.
pronunciation.
You never do that.
And yeah, and then all the times when I decide that my question was terrible, we need to go back and ask a different question. Yeah, and all the times that someone shows up at the front door, and so someone has to go and sign for a package. So yeah, so that's what we'll get to today, and then we'll stick around for a few minutes afterwards, and people can ask us some questions. Now you'll hear me say that it is for May 13th. That's because we're still catching up.
I have their CDs right here. They're a group that does soul music that is science bent. I just love the twist of that. We're still working to line up some additional musical guests. We're going to have Mad Art Lab's Death by Puppets. We're going to do a virtual star party. We're going to bring on the cast of Beyond the Wall to try and figure out what the heck is this science that explains the weather of Game of Thrones. And it looks like our 24 hours is actually going to be 36 hours.
Oh,
Our
come
goal.
on.
Well, we keep getting this great outpouring of people who want to help. And yeah, we usually call that a normal weekend, staying up that long around here.
Right.
And we're also going to be releasing the latest version of the CosmoQuest interface. So it's going to be a crazy weekend, and that's going to be co-hosted by Nicole and I. We're going to be having you come on a bunch, and it should all be good.
You know what's funny? I don't see all of the times that you want me to do things, which makes me feel like you plan to have me show up at all kinds of times. So
no, so we haven't finished booking everyone yet, and you have a flexible schedule.
And, so
you're on the to be scheduled last.
Sure, no problem. And I know we might do some stuff at night with some astronomers, and we might also do some stuff during the day.
Yes.
And sometimes someone's day is another person's night. So I think maybe try and catch a live ISS pass, things like that. So
yeah, and I'm switching cameras just to warn you. Switching that sort
What?
of worked.
Why'd you do that?
Because this camera is the camera that you prefer, except it has a crazy tilt and is just out of arm's
Yeah, and
reach.
your video has frozen.
Oh, it did?
For me, anyway.